All right, I'm back, man.
Okay. Thanks for coming by.
Thanks for having me, dude. And by the way, I know I told you before in the emails. Thanks for actually caring enough to shoot those pictures to me at the beginning. All right.
Yeah, no problem.
And check this out. Real quick. I didn't injure my hands, both my hands. I injured my left hand.
Okay.
I fought with the ground and lost. But yeah, dude, what in the world? Oh, there we go. Yeah, dude, if you can see my hand at all. It's not swollen like it was or anything. But
yeah, I see a bit.
It's still a little messed up. But yeah, man. Well, alrighty, let's get this rolling, sir.
Okay. So did you want to start with me going through the pictures and the analysis that I did, or did you want to start somewhere else?
No, we can start there, man.
Okay. Let me get those pictures into the window that I'm sharing. Hang on. Right, save that one. And by the way that I figured out where you were when you took that picture, I'm not a magician. All I did.
Well, I realized it's in the details of the photograph I sent you. I
exactly.
Yeah.
So it wasn't.
Well, no, I was mainly talking about like the angles and everything that you were throwing out, because you were pretty much spot on. Not bad.
Yeah. But once I knew where you were and what time it was, I entered it into Stellarium, to get an idea of what your actual direction was.
Oh, if I would have known you were gonna do that, dude, I would have flat given you my address, because I was standing in front of my house in the middle of the street.
Gotcha. All right, so I'm saving the pictures. I'll be ready in about one more minute.
No problem, man.
Okay. Let's go here.
And I noticed the first thing that people have thrown out when I've shown them that, and I'm talking people that believe in a globe, because they thought it was my pictures. And so they obviously, because they thought it was mine, they started picking it apart.
Mm-hmm.
And they were saying, well, there's a problem because it's not to scale. And obviously I heard from the quick show you had earlier when I wasn't here, that apparently you did hear Steve McRae's, right?
Yeah, I watched that.
And that's really what it came down to with them. That was basically their answer at the end of it was, well, but it's not to scale.
Mm-hmm. Okay.
Which I've been trying to look at a way of where I can find out how to possibly rig like at least some kind of scale model.
Right. Okay. So let's start with the photo that was taken by Mike Solway in 2009 from Australia. So for other people, we have the moon, we have Mercury, Jupiter, and Mars. And we have the date down here, 23 February 2009. And he's taking this, I think, from just north of Sydney, Australia. And so this is not to scale, and this is zoomed in and whatnot, but this is more or less what the solar system looked like at that time. And the program that I'm using for this is hosted by Formulab. So I'll put the link in the chat if people want to follow along at home. And the date for this, again, is 23 February 2009. And it would have been about 2 hours before sunrise Australia time. So that might actually be the 22nd or the 24th of February. I don't know for sure. But anyway, so it's true that Venus and Mercury their orbits are inside of Earth's orbit as far as the order of the planets goes. But we don't have to be looking away from the sun in order to see the planets that are orbiting outside of the Earth's orbit. So, for example, on this day in February 2009, when the photographer took the picture, he was standing somewhere over here. It's kind of hard to see exactly, but he's standing somewhere over here, and he's looking, and he sees Mercury, and he sees Mars, and he sees Jupiter. He's not yet on the side of the Earth facing the sun. He was about 2 hours, I think I said in the email, about 2 hours before sunrise. And so 2 hours is 30 degrees because 24 hours is 360 degrees. So he was about 30 degrees away from
1,000 miles an hour, right? That would be roughly 2,000 miles in from the Terminator line, right?
If he were on the equator, yes, but he was below the equator.
Gotcha.
Right. It can be easier to think of these things not in terms of the miles, but in terms of the angles, because the angle is going to be the same no matter where you are on Earth. Like just because the equator is, let's say, 24,901 miles, so that means on the equator, every every degree on the equator is a certain amount of distance. And when you're down in Australia, every degree around, what is it, like 40 degrees south latitude, every degree around that is a shorter number of miles, but it's the same degree. So he was about 30 degrees in from the sun, from the Terminator line. So the other issue that we have to remember is we're looking right now at a 2D picture of something that's actually three-dimensional. So
yeah, I get that.
So the problem is not that, like, if he's over here, he's not looking through the Earth because he's standing on a part of the Earth, and he doesn't need to look through the Earth to see the sky above him. So he could actually, for all intents and purposes, he could be on the northern hemisphere rather than the southern hemisphere, and he would be looking not through the Earth, but simply into the half of the celestial sphere that he can see from his location.
And that's what I'm trying to actually work out right now with like, I understand that he's not I get that you're trying to say that he's not looking through the Earth, but
right, he's not looking through the Earth, and he's not yet looking at the sun because from where he is on Earth, the sun hasn't risen yet. The Earth, from where he's standing, he hasn't turned past the Terminator line. And one thing that the heliocentric model tells us is that because Venus and Mercury have orbits closer to the sun than Earth, there are only certain times that we will ever be able to see Venus and Mercury. We can't see them when we're staring at the sun because the sun's light is too bright and it illuminates our atmosphere too brightly for the planets and the stars to be seen. One thing we know in the Northern Hemisphere is that Polaris is, for all intents and purposes, stationary. So as soon as the sun has set enough that you can see Polaris, the North Star, until the sun rises again, you're not going to see Polaris move more than about a degree from where it is. It's going to make a very, very small circle. And what this means is that even after the sun has risen and the sky is now too brightly illuminated to see the stars, we still know exactly where Polaris is, even though we can't see it. And so there are times when the other planets are in our sky, but we're simply not able to see them because the sun is illuminating our atmosphere too much for us to perceive them. So there are limited windows of opportunity to be able to see Mercury and Venus. And it's essentially, the technical astronomical term has to do with their greatest elongation, which is basically when the angle between Mercury, the sun, and the Earth, or Venus, the sun, and the Earth, when that angle is at the maximum that it can be for us to be able to see the planet in our sky. So yeah, basically, we can't see them more than a couple hours after sunset and more than a couple hours before sunrise. Because as you would point out, otherwise we'd be looking into the night sky in the other direction, and we can never see them when it's midnight. You know, we can never see them when we are 180 degrees facing the opposite of the sun. And we can never see them when the sunlight is so much in our atmosphere that the sun is too bright for us to see anything else. And so the same situation goes for your observation of Venus and the moon. I know that you've said, you know, for all intents and purposes, it looked like the sky was pitch black. But you were only about 2 hours away from sunrise. And if you open it up in Stellarium, you can see how close the sun really was to the horizon. And that meant that that time that you saw Venus was within that brief window, probably like 2.5 hours, you had a window during which to see it. If you had gotten up maybe 45 minutes earlier or maybe an hour earlier, you would have been able to see Venus rising. And you would have been able to time how long from the time I see Venus rise to the time that I can't see Venus anymore. How long is that? And that, in and of itself, would help you determine what the angle between the sun, the Earth, and Venus was at that exact day. So again, this is more to scale. I mean, it's not perfectly to scale, but again, this shows you here's Earth, and here's Venus, and here's the sun. Oh, but can you see my mouse cursor, by the way, or can you only see my browser window?
No, I can see your mouse cursor.
Okay, good. So depending on where you are on the Earth, you are still able to have a line of sight to Venus. But again, as the Earth turns and as you get into the sunlight side of the Earth, then the sun's light will be too bright. And let me just make one more comment before I turn it over to you. I should have mentioned what the blue and the green parts of these orbits meant. I didn't mention it in my email, and I know it came up in the Hangout you were in, and it was a little bit of a confusion for everybody there. The green and the blue parts of the orbits simply represent when the planet is below the Earth's orbital plane and when the planet is above the Earth's orbital plane. Because basically, because we're on Earth, we treat the Earth as having a flat elliptical plane around the sun, and all the other planets, their orbits around the sun are slightly tilted. So I think the green represents when the planet is below our orbital plane with the sun, and the blue represents when the planet is above our orbital plane of the sun. But that information is completely unnecessary for our exercise. It's just something that
No, actually, that's something I wanted to ask you over the last couple of days. I think, you know what? I think I remember now that you were watching Steve McRae's debate. Because did you type in the chat exactly what you just told me right now, basically?
I don't think I was watching it live. I'm almost certain I wasn't watching it live.
Okay,
Oh,
then
wait.
someone knew exactly what you had done with the different colors. Because when I went back and I was watching the video, the live, or not the, when I was watching the chat afterwards, and I was able to see the live chat recorded, I saw that someone had posted in there what was going on with that.
I might have left a comment after the video, but I'm almost certain I wasn't watching it live.
But okay, you said that the green is when it's below and the blue is when it's above?
Yes, so it says here, the portion of each orbit above the plane of the ecliptic is drawn in blue, and the portion below the ecliptic is drawn in green. So what that means is, for example, here, Earth is always perfectly in line with its own ecliptic, its own orbit around the sun. So during this green part, Venus is, for all intents and purposes, tilted below the sun, and the blue is when Venus is above the sun from the perspective of our orbit around the sun. This doesn't, I mean, again, it doesn't really factor into the conversation we were having. It's just a piece of information that this particular orrery provides. And you can see a better visual representation of it in this orrery. If I get perfectly in line with the Earth's orbit, you can see that these other orbits are tilted. You know, they have an angle. Yeah.
Kind of like if you're watching a plate as it was spinning when it goes to stop and you see it wobbling before it actually stops.
Exactly.
Down. Yeah, I get you. And so then on that picture that I showed you at first with the Mercury, that one right there.
Yes.
That, okay, so where I'm trying to understand where you would say, because I understand the guy's in the southern hemisphere, right?
Mm-hmm. Right.
He's in Australia. By the picture that you sent me with the blue and green rings,
Mm-hmm.
that means that Mercury, Mars, and Jupiter would be below the line of the orbit of Earth in this image.
Right. They're below the ecliptic. Now, I think because he's in Australia, that means that we would actually draw the line of the ecliptic beneath them. I'd have to open Stellarium to know for sure. It's difficult for me to think of these things coherently because I'm so northern hemisphere bound. But let me try to pull it up in Stellarium real quick and see if I can get an answer for you.
And Jeff, hey, thank you very much for going over this with me in a very civil manner, dude.
I think that the whole flat Earth, globe Earth situation is way too violent and derisive and just it's not the kind of environment that I like to be in. So when I do these conversations, I am courteous, I am polite, I don't use profanity. I don't know who's watching. And I try to be as respectful of my guests and my audience. So I'm incredibly happy that you are willing to be as polite and calm and respectful. It's a welcome change.
It was the way I was raised, right? Like, seems like something lost on society nowadays.
I will agree that it is not. It is far less common than I would certainly wish it was. All right, so I'm going to try to get this. I'm not sharing my screen. I'm only sharing a particular window. So you may simply have to take my word for it, or maybe I'll take a screen capture. But let me figure out how to get. Oops, not March, February. February 23rd, I think it was. February 23rd, 2009. Let's find the moon. Okay. Ah, crap, it's the wrong year. So while I'm doing this, is there another topic you'd like to move to? Or
what would you like to get into, dude? Because, I mean, hell, we could probably get into all kinds of stuff, man. For instance, I've been thinking about doing a little project where I want to launch a like a 10-foot, 1 millimeter thick mylar balloon. I want to see how high it goes.
sounds like fun to me.
Because rumor has it they can go like 1,000 miles.
Mm-hmm. I'm going to take a screenshot of Stellarium right now. Just a second. Screenshot. Now let me hopefully find it. Okay, can you see this?
Yeah.
Okay. So this line here that goes through E horizontally, this is the guy's horizon. I have the ground turned off.
Okay.
And the this is the path the sun takes, this particular blue line here. And because he's in the southern hemisphere, that means the things that are on this side of that line are below the ecliptic. And so it does seem to indicate that Mars, Jupiter, and Mercury are below the ecliptic at this particular date. It also shows that the moon happens to be below the ecliptic. The moon, I don't know if you know this about the moon, but the moon's orbit around the Earth is also tilted 5 degrees. So sometimes it is above the ecliptic and sometimes it's below the ecliptic, but it goes through that cycle every 27 point, I don't know, like 2-3 days. So at this particular time, the moon was below the ecliptic as far as Earth is concerned. Okay, so I've talked for long enough, and I said in my email that I think it would be fair if if I take a topic and then you take a topic and we discuss it until we're, done with that topic. So let me give the Hangout window to you, and now you can feel free to bring up whatever topic you would like.
I actually like what we're talking about now, because
Okay. Sure.
I was just talking to someone about this like a day ago regarding that picture in which you had pulled up with Stellarium right now.
Mm-hmm.
So I'm trying to visualize in my head where in the heck that guy could have been standing okay.
Mm-hmm. All right, let me put the ground back on. Can you see my Stellarium window now?
Yeah.
Okay. So the research I did to find out where he was is I went to his blog, Mike Salway, and I went to the link that I will put in the chat right now. So that is where his photos are. And he mentions on that blog post, I finally decided to head to Berkeley Vale on the west side of Tuggerah Lake, which has a few nice wharfs. So I think I looked up either Tuggerah Lake or the other place, Berkeley Vale. So he's in New South Wales, New South Wales, Australia, which is like northeast of Sydney. It's in the vicinity of Central Coast, Australia. But so that gives you a general direction of where a general location of where he was. And then the direction he was facing was more or less due east, somewhere around 8 degrees south of east. And I can determine that based on what he sees in his photos, and where the heavenly bodies happen to be located at the time that he took the picture. We can see from his pictures, and he took multiple pictures, which is great, and he made he had some excellent photos. One of his photos shows the early stages of dawn, but a couple of his photos show it considerably darker in the sky. So that gives us an idea of what time of day it was, like how close to sunrise it was. So, it was somewhere around this time, which was like about 5:15 local time for him in the morning. I don't remember if he actually says in his post what time it was, but I pretty much deduced it from when he said he took the photos and where the things were located. And if I turn on the animation again.
No, what I'm wondering right now is if he's standing there and looking in that direction, in which direction is he spinning with the Earth? I might have said that wrong, but do you get what I'm trying to say? Like,
I think
spinning
so.
Where what's in front of him would be coming towards him, or is he spinning where it would be going at an angle? Or
well, what we can do is we can turn the animation on, and we can see that what he's seeing is moving up and towards the east, more or less. Okay. So again, I'll rewind. Whoa, crap. Okay. Okay. So these are the things he's observing. The moon, Mercury, Jupiter, and Mars. And we can see that, and again, remember, he's in the southern hemisphere. Okay. He's facing east. So he is facing the direction that the Earth is rotating, because the Earth rotates from west to east, which is why we see the sun rise in the east, because we're rotating towards the east. So if I stop sharing, well, okay, so I'll just, again, animate this just a little bit so we can see he's seeing these things rise in his view. And then the sun rises. So now if I go back, if I stop sharing that screen, okay, and I go back to sharing my browser window, what that would mean is he's on, you know, I guess we could say he's on the bottom left-hand corner of the Earth here, if you can see that. He's on the bottom left-hand corner of the Earth, and he's rotating, as far as we're looking down on it, it would be as if he's rotating counterclockwise. So he's going from where he is here around the bottom like that. So that's what that's the motion of the Earth. So he's coming from here around like that. And again, it would be easier to visualize this if I had a 3D model, but again, we're looking at a 2D model of something that's three-dimensional. So it can be tricky to figure it out spatially. And again, because he's in the southern hemisphere, the things that he sees above the ecliptic are actually below the ecliptic, because he's looking at things, as far as we're concerned, upside down.
Okay. Okay. And then in regards to things being upside down.
Mm-hmm.
Give me 1 second to pull up.
Sure.
There we go. Now what happened to my Hangout screen? There we go. Okay, so I understand what everyone tries to say about gravity, right?
Mm-hmm.
I get that.
Well, I don't know.
Well,
I will assume.
Okay. Here, let me just go into this real quick. All right, so let's say that I am up here on this globe right here, right? Mm-hmm. And I realize this is not an accurate representation.
Yeah.
But this is just to kind of prove a point.
Sure.
So if I'm like right here, if you can see my cursor, mm-hmm. and I get on a plane, mm-hmm. I'm basically right side up, right?
You're always right side up, but yes, you are right side up.
Well, hypothetically, if we had a space station out, let's say 500,000 miles or so, do you think 500,000 miles would give you enough range to be able to see the whole Earth?
I'm pretty sure we can see the Earth from 1,000,000 miles away, Sure.
Yeah,
Let's say
the
we
epic
can see it.
satellite. I've seen that with the moon passing in front and all that.
Yeah. So let's say, for the sake of argument, sure, we can see the whole Earth from 500,000 miles away. I'm fine with that.
Okay. And let's say you're like on a space station and you're looking through a high powered telescope at the Earth,
Mm-hmm.
and you watch a plane take off from here
Mm-hmm.
and then fly down here to some island.
Mm-hmm.
Did you not just watch somebody that's right side up end up going upside down?
Yes, you watched a person go right side up to upside down, assuming that your orientation right now in the space station is such that up for you is the North Pole and down for you is the South Pole. I
Well,
don't want to
just going
digress
off of
too.
this picture,
Right.
this looks kind of like Australia, so I'm
Yeah.
guessing they're trying to say that this is down and this is up. So if you're here right side up and then
Mm-hmm.
you end up down here and you're going around a ball, technically, did you not just end up upside down? Like physically, you seriously went right side up to upside down, did you not?
To an external observer, yes, you do. From a person floating in, no, you see, like, this is why the term relative, which gets a bad rap, is very important. If I am a person 500,000 miles away from Earth, floating in space, looking at the Earth the way it appears right now on your Hangout window, for me personally, up is where my head is, and down is where my feet are. And so everything that I observe, I'm going to say up is the direction of where my head is, and down is the direction of where my feet is. So when I see through my high power telescope a plane take off from somewhere near Siberia and land somewhere in Australia, from my perspective, that person and that plane is now kind of upside down. It's kind of on it's kind of like sideways now. The reason is because from my frame of reference, from my, and I don't want to use the word perspective because perspective is a very loaded word. And whenever I use perspective in these conversations, I always want it to mean the law of perspective, how things change in size based on their proximity or distance from you. So I'm not going to say perspective. I'm going to say, because of my frame of reference as an external observer, yes, there are things on the earth that will look upside down to me. However, if you are in that plane taking off from Siberia and going to Australia, for you, up will always be the direction your head is, and down will always be the direction your feet is. Or to be more technically precise, up will always be away from the earth, and down will always be towards the earth. Um, so this, and the reason we speak this way is because our concept of up and down on the earth is completely due to gravity. The only reason up is up for us and down is down for us is because down is the direction that gravity pulls us towards the center of the earth. This is why when you're upside down on earth, you know you're upside down because your circulatory system is not used to having to work hard to pump blood out of your head. But when you're upside down, suddenly the blood is pooling in your head because your circulatory system is not used to the pull of gravity pulling the blood down into your head. Your body is used to blood having to be pushed up into your head against the force of gravity. So when you're hanging upside down on a jungle gym or monkey bars or whatever, your body's like, whoa, blood is suddenly going to my head without me having to work hard. So now I need to figure out how to work hard to pump the blood out of my head instead. And the reason is because, again, gravity is pulling the blood in your body down towards the center of the earth. So when you're in an airplane, you're always going to feel right side up unless you hit turbulence and and start, like flying through the airplane. Because down for you is always going to be, for you, towards the earth, and up for you will always be away from you. This is what relativity and frames of reference are all about.
I get relativity, but I don't know. Upside down is upside down. But
upside down is upside down depending on where you're observing from. For example, let's say I have a tennis ball in my hand and there's an ant on the tennis ball, okay? The ant is able to crawl all the way around the tennis ball without falling off of it, right?
yeah.
Okay. From my perspective, holding the tennis ball, if the ant goes from the top of the tennis ball to the bottom of it, that ant looks upside down to me now. For the ant, I might be generalizing here, but the ant, because he's not being pulled off the ball by gravity, because he's able to stay stuck to the surface of the tennis ball, for all the ant is concerned, the ant's not upside down. The ant's just going around a sphere. Now, part of the problem with this analogy that I've just used, and I will always admit the analogies fail because they're not the exact thing being described. The ant is feeling the effects of gravity when he's upside down on the ball. And the reason for that is that the gravity of the earth is pulling him down towards the earth. And he is able to stay stuck to the ball, not because of the gravity of the ball, but because ants are able to stay stuck to things, which is why ants can go up walls and we can't, and why ants can be upside down on a tennis ball and we can't. So this is another place where gravity, which is part of the modern mainstream model of the universe, one of the problems with gravity is that we can't ignore it. We can't really overcome it. I can't make a model of the Earth that has water sticking to it because that water is going to be attracted to the actual Earth because of gravity. The only way I could make a realistic model of that is to go far enough away from the Earth's gravitational pull that I could make a model ball with enough mass that its gravitational pull on the water that I place on it keeps the water onto it. And again, like, this is part of the problem of gravity, is that we can't assume it away. Like, we can't make a physical model of something that is able to ignore the Earth's gravity. And the reason is because the Earth is so massive that its gravitational pull on whatever we make in our model is going to mess with our model. There's no sandbox for us. There's no clean room that we can ignore gravity. The only way we can ignore gravity is to be in free fall, because then, as Einstein will say, bodies in free fall are, for all intents and purposes, staying still. And that's a completely bizarre concept, and I don't really want to digress and get into that.
So on the note of gravity, real quick, which would you say is more powerful, gravity or a vacuum?
Do you mean a vacuum cleaner or a vacuum?
A vacuum, like a complete vacuum.
I'm going to say that the force of gravity depends on your distance from the object that is creating a gravitational pull, and that eventually you, or let's say, instead of you, let's say the atmosphere of the Earth could be far enough away from the center of the mass of the Earth such that it is kind of in an equilibrium between the gravitational pull of the Earth and the vacuum of space, which it is leaning right up next to. I know this is a, I don't want to say a talking point. I know this is a common line of argumentation, which is essentially, how does our atmosphere not just get sucked up into the vacuum of space? And the reason is that the vacuum of space is not a vacuum cleaner. It's not something that's constantly sucking on the Earth's atmosphere, trying to take it away from us. The vacuum of space is simply space that has nothing in it. That is what a vacuum is. It's not a place of negative pressure. It's a place of no pressure because there's nothing in it. And the atmosphere that we have extends into space as far as it does because of the gravitational pull of the Earth. And this is why, for example, the moon has no atmosphere. The moon's gravitational pull
Watch out with that
is
one,
not.
Jeff, because they say that the moon does have an atmosphere now. I've seen people say that. Not flat earthers. I'm talking about globe believers, man. Arguing
Well,
with flat earthers.
I
Like,
can't speak to that. I have no knowledge that the moon has atmosphere. All that I've read about the moon has said that the moon is not massive enough to have an atmosphere.
that's what I thought, man.
Mars has an atmosphere, but it's very thin. Again, because Mars is not massive enough to hold a thick atmosphere to it. So that is how I would address that particular line of argumentation, that our atmosphere extends as far away from the Earth as it does because of the gravitational pull of the Earth, and that there is a boundary line. It's not a physical boundary line. There's simply a point where if something is there, if that gas of the atmosphere is there, it's there because the Earth's gravitational pull still pulls it to the Earth more strongly than the vacuum of space can attempt to coax it away from the Earth. That's probably not the most scientific language to use.
Oh no, you hit the nail on the head. Exactly what I thought. I don't want to say what I thought you were going to say, but that's really actually, believe it or not, that's not exactly where I was going with that one. Believe it or not, I get tired of the same arguments that I hear because it seems like everyone's just going round and around, and I just think, can't we get different arguments, better arguments? Can't we improve on the arguments we're using? You know, isn't that what I thought? That's what science kind of was, right? I thought.
I'll agree with you to a certain extent. And I do apologize then for if I was putting words in your mouth by answering a question that you hadn't actually asked yet.
Oh no, it's not, you weren't putting words in my mouth. Actually, you hit on a great point. It does tie into this, but what I was thinking about was, because it's kind of funny because this is flat earthers that threw this rebuttal at me. Okay. I brought up to them, I was talking to them about, you ever seen that trick where you take like a bottle of water and you fill it up and then you put like a business card on it and then flip it over on its head and
then you
take your
slide
hand away from the business card and it stays there?
Yeah.
I was talking to them about that and they're like, well, that's just the vacuum. And I started thinking about that and I go, well, how much of a vacuum could it really create inside that little bottle? And is that vacuum really stronger than gravity right now? Because you can do that with like a gallon of water, you know? And a gallon of water is pretty heavy, enough to where it should have been being pulled. But I mean, if that vacuum is that strong, I was just wondering, like, which is stronger, a vacuum or gravity? That's all. that's kind of where I was going with that one.
Right. And I guess I would say, like, it depends on the strength of the vacuum, because you can even do this without water. Like, once you introduce water, then, like, you could say, well, one of the factors is there's water tension and whatnot. But you can do a similar exercise, which is if you take a water bottle and you empty it of water completely, and then you put it up to your mouth and you suck out some of the air into your lungs. And then very, very quickly, you take the water bottle away from your mouth and put your hand over it, making a seal. If you do that quickly enough, and if you've sucked out enough air, okay, the water bottle, the empty water bottle, will be suctioned to your hand. And then you can essentially defeat gravity, because the force of that suction, the force of that particular vacuum, is able to overcome the force of gravity on that water bottle.
And that's an empty bottle, though. That's really light. I'm trying to handicap myself with having like at least a pound of water on top of the card, and it's still being held up.
Right. And therein is the issue. The more massive an object is, the greater the force of gravity between it and the Earth will be, which is why you can do this trick more easily with, say, a plastic water bottle than you could do with a solid crystal drinking glass. You could still do it. You would need a much stronger suction. You would need a much stronger vacuum seal on that glass. And you might find out that even with that suction, even if you keep your hand perfectly still so that you don't mess with that seal that you've created, you might find that gravity is working on that heavy crystal goblet, and it makes it fall. Not because you broke the seal, but because gravity was able to break the seal. And so this is why sometimes the vacuum is stronger than gravity, and sometimes gravity is stronger than a vacuum, because gravity depends on two masses and the
So if
distance
you have the
between.
mass of the water, though, and the mass of the Earth, wouldn't that actually be a stronger pull of gravity than an empty water bottle that's suctioned to your hand?
Correct. And so
So
all this,
that would be.
I'm sorry, keep talking.
Oh no, I was just saying that would. To me, that would almost be like a handicap with the water in there.
It is a handicap, but what, like, you do have to simply accept that you can create enough suction, even with that weight of water, to overcome temporarily or locally the force of gravity. And you might find that that suction holds for an hour or two or three, and then it suddenly gives way. Or you might find that it holds indefinitely, or until the business card soaks through, something like that.
Actually, it's usually when the business. You're right. It's when the business card soaks through.
Right, and that's why, like, using water is sometimes a bad example, because using water introduces all these other variables in the equation. But you do need a fluid substance, whether it's a liquid or a gas. You do need a fluid substance, because you need something that's able to create that seal. You couldn't reproduce this with, like, a water bottle full of sand, because the sand particles are not fluid in the way that actual fluids are fluid, and so you couldn't actually create that vacuum seal to begin with.
Yeah,
But I
that's
suppose if you took a laminated business
what?
card,
Actually, though, thinking about that, I, okay, I don't think you'd be able to fill up the bottle, but I think you might be able to actually create like a vacuum with sand inside the bottle, but it wouldn't be, it would not be able to be dry sand. So never mind. You're right.
yeah,
It wouldn't be able to, it would have to be like wet sand, and then it would only last until it dried. And then once it dried, it would start crumbling. And once it started crumbling, there goes the business card. There goes all the sand out of the bottle. So yeah.
yeah. You could use a laminated business card, one that doesn't absorb water, and that would be a good way to test that experiment. But yeah, like, as much as flat earthers argue about gravity, and I've seen ridiculous arguments like gravity strong enough to hold the water of the earth, but too weak to hold a butterfly. Well, a butterfly is far less massive than the oceans, and the amount of force that a butterfly needs to exert to temporarily overcome gravity is very little. But of course, a butterfly has to continually create that force to continually overcome gravity, which is why, yeah, we can overcome gravity when we jump, but we'd have to continue jumping repeatedly in order to not fall back down. We'd need to keep flapping our arms or our wings or whatever in order to stop gravity from pulling us down. The oceans are so massive that it takes a tremendous amount of force to lift them up, to make them overcome the force of gravity. And even when the tides occur, yes, the tides, like high tide, means that the water is less under the effect of the Earth's gravity by a minute fraction, because the moon has lined up directly over them, and so the moon's gravitational pull is ever so slightly greater. The tides are not really as amazing as we make them out to be, because the tides are a matter of, I don't know, a dozen or 24 meters, maybe. And in the grand scheme of things, in the depths of the ocean, a dozen meters or so is not a tremendous amount of movement.
So obviously you subscribe to the moon is what's causing the waves in the water.
I don't think the moon causes the waves. I think the
Or
moon and the sun
not the
are
moon, but the
responsible for
gravity.
tides.
The gravity, the pull of the gravity on the water with the moon spinning around is causing the water to move, right?
Right, because all of our, I don't say our meaning my, but scientific observation indicates that the tides are highest when the moon is directly above, and the tides are weakest when the moon is 90 degrees to the body of water. The tide is also relatively strong when the moon is on the complete opposite side of the Earth. The tide is even stronger when the moon and the sun are aligned and whatnot. So yes, I ascribe to the theory that the tides are caused by the gravitational pull of the sun and the moon on the waters of the Earth.
And so then, like, giant lakes are just, they're not big enough bodies of water to have that gravitational pull, is basically
I have heard that Lake Superior has possible tides of a couple of centimeters, but it is
heard about that
difficult.
too.
But it's difficult to know whether these are actual tides or if they're simply like local observations of the ebbing and flowing of the water back and forth from winds or from other factors.
It's funny that you say that, because someone threw that out at me about the lakes in Michigan, right?
Mm-hmm.
And they sent me a video. And so I looked at the video of what they were showing, and it was somebody on the side of the lake, and they were showing and they were pretty good size. They weren't a couple centimeters or anything, man. They were like 3, 4, 5 foot waves. Like they were coming in. And but the problem is when you turn the sound on, you couldn't hear anything the person was saying because they had like 75-mile-an-hour winds.
Yeah. And that's why I don't think it's can you see what let me share my browser window again for a moment. And the font here is kind of small, so I'll read what I'm reading here. I'll post this link in the chat window. True tides, changes in water level caused by the gravitational forces of the sun and moon, do occur in a semi-diurnal, twice daily pattern on the Great Lakes. Studies indicate that the Great Lakes spring tide, the largest tides caused by the combined forces of the sun and moon, is less than 5 centimeters in height. These minor variations are masked by the greater fluctuations in lake levels produced by wind and barometric pressure changes. Consequently, the Great Lakes are considered to be non-tidal. So what this means is that you can't simply judge the tides based on the height and frequency and strength of the waves that are coming in, because the waves can be caused by any manner of things. The tides are an actual pulling, an uneven pulling of the body of water. And I can show a little image here. One moment, please. Algebra. Let me pull up a little model that I created. Okay, here we go. Can you see what I'm sharing still?
Yeah. I see a graph in the corner right there that says tides debunk.
Yeah. Now it should be full screen.
Yeah.
Okay. So this is not a very to scale drawing. This is supposed to represent, this is the western shore of the Atlantic, and this is the eastern shore of the Atlantic. Okay. I have this blue body of water, and that represents the Atlantic Ocean. And you can see from the area here, it's 0.226. It's the same area as this body of water. Okay, so the amount of water in these two images is the same amount. Okay. This top image represents the Atlantic Ocean perfectly still with no tidal forces on it at all. Okay.
Okay.
The bottom represents the Atlantic Ocean with tidal forces in play. It is high tide on its western shore and low tide on its eastern shore. Okay. Now, what this means is that sea level, okay, so if we look at this top again, sea level on the western shore and sea level on the eastern shore of the Atlantic Ocean are the same height, right?
Mm-hmm.
Like sea level is sea level, okay? During high tide on the western shore, sea level is now a bit higher than sea level on the eastern shore. And the reason is because the Atlantic Ocean is under the influence of the tides, and so the water level is actually higher on the western shore than on the eastern shore. And this water has to go somewhere. Now, we know that on Earth, all the oceans are interconnected. So, you know, the water that swells during high tide is being pulled away from some place that's experiencing low tide. Well, what this means practically is that the water is slanted between the western shore and the eastern shore of the Atlantic. The water, which, if there are no waves in it, yes, the water is flat, but it's not actually level because sea level is higher here than it is here. The sea is not flat. The sea is not level anymore.
I get what you're trying to represent right here, man. It's kind of, I don't know, maybe it's just in my mind. It's more of like you're saying, the top is level and flat, but it's smaller on the right side than it is the left side. It's almost as if like the water, it's like the top is level, and as the water comes up on the tide, it's coming from like below where it, like below and adding to, that's the left side, I guess.
The contour of the bottom of the ocean doesn't matter because, as we all know, water doesn't conform to the shape of the container it's in. Like the water doesn't go, the water doesn't follow the contour of this. The water seeks to simply fill up and be flat.
Exactly, because if there was a hole right there, it would try to find that hole, right? Like,
right. So, I mean, I could have made this, you know, simply a rectangle. I could have made it look like a swimming pool for all intents and purposes.
Yeah.
And so what this indicates, first of all, is that if you accept that the tides happen, no matter what you think causes them, then you have to at least accept that the tides cause the water to be slanted on the Earth in some way, even on a flat Earth. A high tide here means a low tide here, and that means that the water is slanted.
Anybody
Now,
who's seen a fat guy get into a swimming pool knows exactly what you're talking about.
now there is sort of an escape clause here, which is that water at rest is level, and the tides are a force being exerted on the water. Therefore, the water is not at rest. And that's perfectly true. However, the oceans are never at rest. And so it would be great if there was a completely isolated, fresh body of water large enough and long enough somewhere on Earth that we could see how the tides affect a body of water that has no other influences on it at all. Like, we would need to shield it from sunlight, from wind. We would need to keep the pressure in the room exactly the same at all times. Like, this would have to be like a mile. I don't know how many miles long, but like
You're talking about some kind of massive, that is a massive project.
right.
Well,
I
and then
mean,
on top, you're talking about keeping it contained and all that. Well, wouldn't that also compromise it? Because, I mean, if you're putting something in between the lake and the moon now, wouldn't that have some kind of play on gravity if you want to put in gravity there?
the ceiling that you put over our 2,000-mile long swimming pool does not block the effect of gravity of the moon, and it would
Yeah,
not be able to produce enough of a gravitational pull to affect the water. And it would be, you know what, it should probably be a dome over it so that it's like
you know
equidistant.
what? Believe me, Jeff. As soon as I said that, I realized how stupid it freaking sounded.
No, it's okay. I don't think there are too many stupid questions. And it's good that in the process of asking the question, you were already able to start answering it for yourself. I find that a lot of people who get into these conversations and debates are not actually interested in trying to think a situation through.
Sorry, I'm thinking of Debbie right now.
I don't think there is any point trying to have conversations with her. She talks and talks and talks, and is I don't want to get into it. Like, there's no fruit on that tree.
YouTube video this, YouTube video that. That doesn't fly. So if I came to you and I was like, hey, Jeff, so I put together this equation. Check this out. And it's got like 7 variables in it, right? And I tell you that 3 of the variables. Are you going to take any stock in my equation that I tell you that I created?
I think you cut out a bit. Could you please repeat the question?
Oh, sorry about that. Let's say I came to you with like, and I was like, hey, Jeff, I put together this equation and I write it out for you. And it's got like 7 different variables. And I can only solve for, let's say, like 3 or 4 of them, right? Before it starts falling apart. How much stock would you put into that equation I hand you? I mean, would you take that and run to the closest like mathematician and be like, hey, check this out? Or, I mean, would you run to like the next astrophysicist and be like, dude, you need to see what this guy has?
Okay, I don't want to put words in your mouth, but I have a feeling you are bringing up Newton's law of universal gravitation. Am I correct?
You know exactly where I'm going with this. Thank you.
I watched a number of your videos, and I tried to do some research tonight by actually looking at Newton's Principia and finding the parts in it where he begins to talk about this law. I haven't actually found his equation or even his proportional statement in the Principia yet. I know whereabouts I'm supposed to look, but I have to read it to find it. So for the sake of everybody following along, in, was it the 1700s at some point, Newton came out with his Principia Mathematica, probably? No. Oh, here it is. Philosophiae Naturalis Principia Mathematica. The mathematical principles of natural philosophy, sometimes referred to as the Principia. This was Newton's major work, originally published in 1687. All right, and in it, among other things, he puts forward his theorem of or law of universal gravitation. Now, before I get sidetracked on that, let me go back to the question you originally asked, so I can answer that first, and then continue. If you gave me an equation that you said represented some law of the universe, and it had a lot of variables in it, and then you told me, I only know the values for some of these variables, but I think this formula matches the observations I've made, I would probably say, well, we need to figure out how many of the variables that we don't know, like, what do these variables represent? So that would be the first step. What do the variables that you don't know, what do they represent? And then, are there ways that we can go about finding values for them, whether they be constant values that the universe has given them, or the creator has given them, or whether they are dependent variables, such as the mass of an object or the distance between two objects. So in the case of the universal law of gravitation, again, I haven't found it actually written in the Principia yet. I've been looking for it, but I haven't found it. I'm going to write this in the chat so that everybody can see. What we basically know is that the force of gravitation is equal to some gravitational constant g times one body of mass called m1 multiplied by another body of mass, m2, divided by the square of the distance between them. So that's the equation that I've just written in the chat there. F equals g times m1 times m2 divided by r squared. Now, again, because I haven't actually found this formula written in the Principia, I can neither confirm nor deny that this is actually what Newton wrote. I have a suspicion, however, that he did not write this. I have a suspicion that he wrote that the force of gravitation is proportional to the two bodies of mass, is proportional to the product of the two bodies of mass, and inversely proportional to the square of the distance between them. And what that would mean is that Newton postulates, or Newton theorizes, that some force, which he calls gravity, some gravitational force between two masses is dependent upon both the quantity of those two masses and is proportional also to the inverse of the square of the distance between them. He says it's proportional to that, but he might not say that it's equal to it. Just like I could say, my interest in the amount of attention I pay to a YouTube video on flat Earth is proportional to the number of attractive women in the video. That doesn't necessarily mean that if there's one attractive woman in the video, I will have 10% interest in it. And if there's two attractive women, I'll have 20% interest. And if there's three attractive women, I'll have 30% interest. But what it means is that as the number of attractive women in the video goes up, my interest in the video also goes up by a constant factor based on the number of attractive women in the video. And so when Newton says that this force of gravitation is proportional to the two masses and inversely proportional to the square of the distance between them, if that's how he says it, he's kind of admitting that there's a factor, which we would call big G, the gravitational constant. There's a factor that he doesn't quite know. He knows that it's proportional to the masses, and he knows that it's inversely proportional to the square of the distances between the masses. But there's some factor that he needs to multiply that expression by. And he doesn't, maybe he doesn't know what it is. And as you point out in a number of your conversations in your videos, it wasn't until the Cavendish experiment over a century later that a value for the gravitational constant was finally attained. Now, again, I have to say, I haven't found the equation itself in the Principia. When I do, I will almost certainly make a YouTube video about it because I find that interesting.
Well, I'm actually subscribed to you now, so when you do, I will see it. I will be looking forward to that.
Excellent.
Because
So
I
what-
see where you're coming from right now. You're basically, and that's actually kind of a fault of mine on this. Is, I mean, yeah, I've dug into looking at Newton and all that, but I like where you're going with that as far as like, okay, where the hell did this equation like start from? You know, and it
Right.
sounds kind of like what you're trying to say right now is that possibly Newton is it that Newton really didn't write the equation out? He kind of posed it as like a word problem?
I have a feeling that's pretty much what it is. Like, if you look at the Wikipedia article on Newton's law of universal gravitation, you don't see an actual formula described until you get down to the section called modern form. This is what the formula looks like today. This is the modern form. But there's another article that I found somewhere else, I don't remember where, that shows not F equals G times M over R squared,
I've seen a different variation as well.
but rather it shows F is proportional to M times M over R squared. And so again, like I, on my other computer, not the one I'm on right now, I have the Principia open to the section, and I'm going to start reading it, and I'm going to try to find, does he like write it in prose? Does he write in words? And therefore this therefore this universal gravitation is proportional to the product of the masses and inversely proportional to the distance between them. Is that how he writes it? And if that is the case, then like we have to use what Newton actually wrote and not what we know now. And so now, if I could get into the Cavendish experiment just a little bit, because I'm pretty sure that's the next thing you're going to ask about. Like, you know, Cavendish didn't come up with a value for this universal gravitational constant for a century later. Oh, and I will also answer another question that you ask in your videos. The reason why Newton's formula or proportional equivalence, the reason it stuck around is because it was part of a massive book that he wrote that was kind of like the standard for people who were doing the sorts of experimentation and math that he was doing. So it's not that he wrote it on a scrap of paper and put it in a desk, and Cavendish a century later was going through Isaac Newton's contents. He was like, hey, there's this equation here, but he never told me what G was. Now I need to figure out what G is. No, it's that Newton's Principia was this groundbreaking work that lasted for as long as it did. And one by one, his theorems were either taken a step further and proved a little more or shown to be incorrect. So now let's get to Cavendish. The famous Cavendish experiment basically involves four, I'll call them lead balls. There are two very large, massive lead balls, kind of like a big dumbbell. Like, you know, those cartoon dumbbells that the men in the one pieces with the big mustaches, they're carrying these dumbbells that's a really thin bar with two big balls of weight on either end. He has that suspended, and and I'm going to simplify this a bit. He basically has this long dumbbell suspended by a rope, and it has these two massive masses on either end. And then he has two much smaller, much less massive balls of lead, a little apart from one of them is a little ahead of, and one is a little behind the massive ones. Here's a good.
Whoa. Yo.
Okay. We all good? Oops. Right. Okay. So here's a good representation of his experiment. Okay. He has these two heavy masses here, and he has these two lighter masses. And what he's trying to do is determine. Are you still there, by the way? Oh, you're muted. Do you know you're muted? Oh.
Yeah, sorry, man. I'm still here.
Okay.
I had to switch from my computer to my phone.
That's fine. All right, so I'm just going over this diagram. So he has these two fixed heavy masses, and he has these two lighter masses on a barbell suspended by a string.
I've seen that many times.
Okay, and
As a matter of fact, I remember doing that in high school.
you actually did. I never did this experiment in high school. I've seen YouTube videos of people who are trying to reproduce it. I tried reproducing it once in my living room, and I realized like 10 minutes into the experiment that my air conditioner was on, and that was creating air currents in the room that totally nullified my experiment. But so what he's doing here is, instead of having the gravitational pull of an object down, he wants to see if there's a gravitational pull between two objects laterally, perpendicular to the surface of the Earth. And so he makes this setup as you see here. And the purpose of the experiment was to see if you have this wire that doesn't want to spin, torque on wire resists twisting. Okay? If you have this setup that wants to stay still, because a body at rest wants to stay in rest unless a force is applied on it, well, he's checking to see, is there a force applied on these freely moving smaller masses towards these fixed heavy masses? And what his experiment is said to have shown is that the smaller masses were attracted to the larger masses. Now, we need to make sure that we factor out things like air currents, pressure changes. We also need to make sure that we're not dealing with any latent magnetism, because obviously, if these substances are magnetic and they have a magnetic field and they're drawn to one another, well, you haven't proven gravitation, you've proved magnetism, okay? It is my understanding that the Cavendish experiment ruled out things like magnetism and air currents and whatnot. And it was in doing this experiment and knowing the masses of these objects and knowing the distances between them that he was able to compute a value for big G, the gravitational constant. Now, as you also point out in your videos, when other people have computed a value for G, the universal gravitational constant, sometimes they get a different value for G. And I would say, I would agree with you. I've seen the Wikipedia article that explains that the value for G has been calculated differently from time to time. There is a current accepted value for G, which differs from the value that Cavendish measured. And so what I would say in this regard is, whenever you are making a measurement or a calculation, You need to worry about your accuracy and your precision. Accuracy is how close you are to the actual value, and precision deals with making multiple tests and seeing if those multiple tests keep giving you a consistent value. For example, if you're playing darts and you hit the bullseye with one dart, that was accurate. But if you hit the bullseye on one dart and miss the bullseye for the next 20 darts, that's not very accurate, right? You only hit it once out of 21 times. Similarly, if you're playing darts and you can always hit like the double one spot on the dartboard with every dart you throw, you have great precision. You can hit the same place every time. And if that's where you're aiming, then you're also accurate. So the question I have is the reason that G is determined to be different values from time to time, is it due to flaws in precision? Is it due to flaws in the accuracy of the experiment being done to compute the value? For example, like if you have these, if you know the masses and you know the distances, one mass is 1 kilogram and the other mass is 500 kilograms. Well, if you remember from your high school physics class, significant digits, significant figures are important. If your precision is simply to the kilogram or to the gram, you can't really be more precise than that. Like if you say this thing weighs 1 kilogram, you can't really deal with numbers that deal in milligrams. You only know this weighs 1 kilogram. You don't know that it weighs 1 kilogram and 3 milligrams also. So when you start multiplying these numbers and dividing by the square of the distance between them, if you know that the distance is 30 meters instead of, for example, 3,002 centimeters, if you just say it's 3 meters, then that again is limiting your precision when you come up with these incredibly important and very small numbers. The G is approximately 6.674 times 10 to the negative 11th. So we have a decimal point with 10 zeros before we get to the 6674. So that shows the size of the number, the magnitude of this constant that we're dealing with. Having precision is very important in measuring this value. And so that is how I would respond to that line of questioning about, like, why do we accept Newton's law of gravitation if he didn't know what G was? And why do we accept this value of G if it's been calculated at different values from time to time? And I'd like to see like a listing, like a chronological listing of the value of G to see, like, are they sometimes wildly different or are they off by a fraction of a percent? Because that's important too. That tells us the accuracy of these measurements. So that's how I'd respond there.
Yeah, I would have to agree with you on that one, because I've seen a flaw with Cavendish's experiment just since the beginning. Even when we did it in class, I would think you would have to take away what it's hanging on to get a true reading on it, right? Wouldn't it have to be? It wouldn't have to be on it. It would have to not be on anything.
Yeah, I think
true reading. Otherwise, aren't you also calculating like the tension, like the tension in the line and everything that you're hanging it from?
I think I would agree with you there. I think if I were to do the experiment, I would want the two smaller weights to be balanced on like a cone. Like the two small weights. Let me go back to the picture, maybe. Here we go. So I would have these two small weights with the bar between them. Instead of having them suspended from something, I would have the bar between them have a little divot, and I would have that divot balancing on a cone so that the barbell could freely spin with no torque or no tension or anything involved. I think that would be a purer way to do the experiment. I don't know if Cavendish made some allowance for the pulleys and the wires. Like I don't know for sure how he did it.
From what I saw, he didn't. As far as him calculating everything, it does say that he did. First off, he waited, like he let it sit there for like a couple days to make sure it was resting completely. And on top of that, what he observed and where he observed it outside of his shed. He didn't even want to be in the shed because he didn't want, like, when you know how if I move my arm really quick, it creates a little bit of a breeze.
Yeah.
He wanted to make sure none of that was in there. So I give Cavendish props on all that.
Right. That's why he used mirrors and everything, so he could observe the system from well away.
Yeah, exactly. And then, but objects in mirrors aren't always what they appear.
Well, I don't think we need to worry too much about refraction and whatnot coming into play. If he's using more or less a perfect mirror, then what he's observing is more or less what's actually happening in real life. Now, again, in our day, we can have a webcam in there, and we don't need mirrors or anything. It can be a completely closed system, and it can be on that kind of seesaw thing that I talked about. And this is why we have an advantage in our day and age. We have this technology at our fingertips now that allows us to overcome a lot of the obstacles that they had back then in trying to compute these infinitesimally small constants of the universe.
Yes.
I just want to give you a heads up. I have maybe like another half hour in me before I really need to stop and go to bed.
You know what? That's no problem with me. I was about to tell you that I got to get off in a minute anyway as well. But
Okay.
This conversation has been great. I don't want to stop the conversation. Yeah, if you want, we can continue chatting at some other point. I find you a very respectable person to talk to, and it's hard to find that in what's going on right now.
I thank you for that, and I thank you for being just as respectful and polite and courteous in this conversation. It is very refreshing and very welcome.
Well, no problem then. How about we get together another time and this will give us some time to look into stuff we talked about right now.
Mm-hmm.
And we can get together some other time and hash things out again.
Okay, I'd be more than happy to do so. I know your schedule. Well, no, I don't know your schedule. The reason I'm free this particular evening is because I was away from my home this evening. I was playing a charity poker tournament, and I'm now staying at my in-laws' house overnight. And I work from home on Wednesday anyway. So, but generally,
but that still means you got to get up at some point, right?
Yeah, I mean, generally, I'm not up until 2 a.m. on a weekday. So
Yeah, no problem.
I don't want you to change your schedule so that we can have these conversations. It would just generally be easier for me if they aren't as late as this one happened to be. But, I'm happy to do the conversations whenever we can both arrange them.
Yeah, no, so am I. And as far as my schedule, I'm an independent contractor. I'm self-employed, so if you throw out a day, if I happen to be scheduled on a day, it's really nothing for me to reschedule what I'm doing, dude. It's really not.
Mm-hmm.
I can find work anywhere with any. Being disabled, man, and so it's kind of cool having my own schedule.
Mm-hmm. Right.
And being able to work when I need to work. So I look forward to talking to you again, though. I'll email you If I don't hear from you for a couple days or whatever, ask you whenever. If you need to do it on the weekend or anything, that's completely fine with me. I'm open.
Okay.
Yeah.
Yeah, and like, in our conversation back and forth in email, and again, I don't want to be dictating the rules of engagement here. I would just like to make sure that we can kind of have an idea of what we're going to talk about ahead of time, just so that we can both be prepared and have our research done or our links ready to show to one another. I just think that orderly conversation is the most fruitful kind of conversation. So,
No
again,
problem. We can. I can get with that. That's no problem.
all right.
That's not usually the way I kind of just go with the flow of what's being talked about. Because
Okay.
things go on tangents.
Yeah, that's fine. And I had a Word document open that I was going to take notes in if we ended up going on tangents. But we did pretty much keep on one topic at a time. But yeah, I mean, I'm flexible. So yeah, whatever works for both of us.
Yeah,
Yeah.
that works completely fine.
Okay.
Yeah, I'm good. I'm good, man.
All right.
All
You have
right.
a good night then,
So
okay?
you too,
Oh,
bro. Have a good night.
all right. See you.